Good morning, class. The end of last lecture gave us a pretty convenient place to stop off. Having looked over all of the binary search tree operations except deletion, we're going to jump into how to delete stuff. And once we have that, we'll know about all of the operations of a binary tree, and you'll be ready to answer some quiz questions about them. When deleting from a binary search tree, the main headache causer is the fact that you have to preserve the binary search tree property. It may be tempting to do something similar to a linked list where like deleting, let's see, I want to make a case where this wouldn't work. Actually, I'll do a case where it would. In many cases, doing something similar to a linked list deletion operation would work. Like if you want to delete 15, you just make 12 point to 17, and it's easy. In fact, the first example we're going to do is even easier. We're going to delete 20. And that's just a matter of setting 21's left child pointer to null. So plain sailing, right? Well, it's going to get more complicated because if you want to delete a node with 2 children, say we want to delete 36, well then our property our strategy of just reusing linked list operations kind of breaks down. What should be the next, or the new right child of 27? Should probably be 32 or 39. But once you choose one of those, what do you do with the other one? But I'm getting ahead of myself. Let's go through the easy cases first. We're going to delete the value 20, and it's a leaf node. Removing it from the tree doesn't change the rest of the structure. So you could just set the applicable pointer to null. And since that node was a left child, we just need to set its parent's left child pointer to null. This is pretty darn straightforward conceptually. Might still be a bit difficult to do in code. Like, you're going to have to keep track of parents somehow. Probably via a strategy similar to linked list operations where you keep track of like a current node and a previous node as you're moving along it. But as long as you keep in mind the relatively simple idea, you'll be fine. Next up is the still pretty easy case. If you have a node that has 1 child, you won't be able to just make its parent point to null, because then 3 will be just sitting there. It should still be part of the structure, but making it so making it so 6's left child pointer is null makes that 3 node inaccessible. The fix to this? That's exactly what you might expect. Just like how on a linked list you would do like the previous dot next equals current dot next thing to make the pointer sort of skip the node we're deleting, we do the exact same thing. 6's left child will become 3. Like that. Here's another example of the same case. We're going to delete the value 15. It has 1 child node, so it's part of this still pretty easy case. And it has 1 child node, so we're going to promote that child node to take its place. So since 15 is a right child, its child is going to become its parent's right child. Like that. The descendants of node 15 don't change. They retain their original structure. You could say that the subtree rooted at 15 looks the same. It's just everything's moved up. And note that little parenthetical. I mentioned that we would have to keep track of what the parent of each node is, and I suggested keeping track of it inside of our deletion algorithm, like just having a local variable for that. But another thing you could do is put a parent pointer inside of the node class, like there we go. We could have something like node parent as one of its properties. Whether you choose to keep track of this data inside of the data structure or only keep track of parents when it's necessary during the delete algorithm is up to you. I would probably recommend not doing the thing I just wrote down, because that could lead to bugs if you ever forget to update the parent pointer during an operation. Comparatively, keeping track of like previous nodes visited during the deletion algorithm is a lot less error prone. Before I move on to the tricky case, I wanted to mention that the child replacing stuff is the same no matter what kind of child the node to be deleted has. Like in this case, we're deleting 15. It has the right child 17, which becomes 12's right child. If 15 instead had a left child, then would that change? Would this left child whose parent just got deleted become a left child of its grandparent? No. It would become the right child of its new parent because the node we're deleting was the right child of its parent. So don't worry about which side the children of the node to delete are on. Okay, time to get tricky. Suppose we want to delete the value 27, which has both a left child and a right child. And we need to make it so once this node is removed, the binary search tree property still holds. So we still have that thing where the values on the right are greater than the values in the center and the values on the left are less than. And the whole thing still needs to be a tree. We can't disconnect any of the subtrees. This might have been an interesting exercise, a thing to figure out on your own, but I'll just spoil it. This is where the successor operation comes in. The reason we learned about that operation, despite its lack of apparent usefulness, is because it turns out to be really useful for this deletion algorithm. We're going to find the successor of the node we're deleting, and then we will take advantage of some properties of the successor. In this specific case, the successor to 27 is 32. This is because it's the smallest node on the right subtree. Minimum value that is greater than the value we're getting the successor of. Which means that it could have a right child. Like, there could be, 34 right here. That wouldn't break anything. But a successor node cannot have a left child. Why not? I'll do a quick proof by contradiction. Suppose it did. In that case, we would have an even smaller value that is still greater than 27. 31 would be the rightful successor to 32. 31 would be the rightful successor to 27, not 32. QED. That's my little proof by contradiction. If a successor had a left child, then that left child would be the successor. Therefore, a successor cannot have a left child. And why is this important? Because, wait, how should I explain this? Okay, just to be faithful to the slides, I'm not going to explain why the lack of a left child is important quite yet. Continuity demands that I first say that we're going to swap the node to be deleted with its successor node. This kind of breaks the tree. At this point, at this point, the binary search tree property is broken. We have a value in the right subtree that is less than the value at the, root of this subtree. And that's not allowed, but it's okay. We can still have invalid states of a data structure during an operation. What matters is that when this delete operation is finished, we result in a valid tree. So, the node to be deleted, remember we set out on this journey to delete 27. It is in the place of its successor, like where its successor used to be. And as we just proved, the successor cannot have a left child. Therefore, it's guaranteed to have at most one child. It could have 0 children, it could have just a right child, but it definitely can't have both a left and a right. Which means that we could just delete it. This sort of reduces to the easiest case or the still pretty easy case. In this case, we can delete 27 by just making 36's left child pointer point to null. I'm going to keep this annotation on because it doesn't spoil later slides. Woohoo! Actually, I guess it spoils the slide after that. I'm going to erase it for the sake of students who are going slide by slide trying to predict the output of operations. Oh, wow, we're done. So that was the cutoff for tomorrow's quiz. I'm obviously going to keep talking because we still have an hour left, but nothing I say is stuff that you'll be tested on tomorrow. Don't tune out because it's stuff that you'll probably be tested on next week. But yeah, this is the study cutoff. May as well talk about the quiz right now. Probably at the time where no more people are gonna come in late. So yeah, quiz tomorrow. there's going to be like 4 or 5 questions like usual. We're going to talk about hash tables and like hash functions and what they're, like what makes a good hash function. Remember that it should be fast and it should hash good. It's hard to sum up in a single sentence, but it's the concepts that we learned last class about how patterns in the keys shouldn't result in patterns in the corresponding array indices. Actually, I got plenty of time, so I'm just going to write down the quiz topics on this slide. Then you'll be able to refer to them later. So we'll cover hash functions, and then the rest of the quiz will be about trees. You'll be quizzed on the... Oh, I have no chance of making a actually good-looking bulleted list. Oh well. These not filled-in bullets are like sub-bullets of the filled-in ones. You'll be quizzed on the definition, kinda. Memorizing the definition might help, but it's not what the question is going to be about. Yeah, I'll stop talking about it now. Don't want to spoil. And then also the insert operation for binary search trees, and the delete operation. Excuse me. So that's all the stuff that's definitely going to be on the quiz. Question? Understand how they work. Basically do an example similar to what I just did. Like, draw the tree after deleting 27. But good question about implementing, because what I just wrote down is all the stuff that is definitely going to be on the quiz. But like, full disclosure, I finalized these at the last minute. I'm no better than a student. So there's still some stuff that I am thinking of changing and may or may not make it in based on time constraints. Last term, a lot of students really struggled with the programming questions on the final exam. So I've been meaning to put a programming question on one of the quizzes so you can like know the rules and mess up in a much lower stakes environment. And I think this quiz might be a good time to put them in. No guarantees that it will be in the quiz. Absolutely no guarantees on what it's going to be about. Actually, I shouldn't say that. It'll be about either trees or hash tables. But just so you're ready, tomorrow's quiz might include a question about writing code. Cool? Yeah?
Is that like the theoretical, we want to implement this ADT exists because X, Y, Z, or is that write in like a paper ADT?
Sorry, what was the last thing you said?
Write out the actual code as if you're in a like paper ADT.
Yeah, the second thing, if this question is in this quiz, it'll be straight up programming, writing code. Okay, let me know either like later this lecture or by other means if you have any questions, but if there are no questions right now, we're going to look at tomorrow's lecture, which I believe will finish up binary search trees. Yeah? Pardon me? Okay, so this isn't really a question. There won't be a question that's just like super generally about trees. But now that I've crossed out that trees bullet point, the 4 bullet points that I have now are going to each have a question dedicated to them. All right, let's keep going. This slide, I think, really should have been at the end of the previous lecture, but we just learned how to delete stuff. There are 3 cases to it, which I'll summarize here. The easiest case is when the node to be deleted is a leaf. That's just like deleting a node from the end of a linked list. You just make its parent point to nothing. The still pretty easy case has the node to be deleted with exactly 1 child node. This one's sort of like deleting from the middle of a linked list. You have to make it so the previous node now points to the next node, sort of skipping the node you're going to delete and thus deleting it. And then the tricky case has no direct analog for linked lists. It's when you have 2 child nodes. And while the first 2 cases were like, they kind of had canonical examples, like you'd be hard pressed to think of another way to delete nodes in those first 2 really simple cases. But in the third case, when the node to be deleted has 2 child nodes, there are multiple deletion algorithms. Our solution was to swap the node to be deleted with its successor, and then take advantage of the fact that the successor can't have a left child, and delete the node from its new position, which now has at most 1 child and thus falls into one of the other 2 cases. So like I said, there are multiple other possible deletion algorithms, but this is sort of the standard one for the course. I'm going to treat this as if it is the only deletion algorithm. So if and when you're solving quiz questions about deleting nodes, you will have to follow this algorithm, because that's the only way the markers can be sure that you know any algorithm and aren't just like deleting stuff off of vibes. So yeah, practice this algorithm for the quiz and the final exam. And we'll be able to do our own practice right here. So we're going to delete the values 25, 36, 18. You can tell that's going to be rough because it is the root node and has 2 children. And 20. Where is it? Easy case. Or is it? We're going to delete those from the binary search tree shown above. "25" is the easy case. or rather the still pretty easy case, slightly complicated because we have to promote its child node. 25 is a left child, so we make 27's left child pointer point to its child. Not too bad. I'm going to recreate that drawing here. So you can still practice on this slide, but then get the answer here. Node 36 has 2 children, so it's by definition complicated. But luckily the subtree rooted at 36 is really small. We can immediately see that its successor is its right child, 39. So we just swap those, and then with 39 in 36's old place, we make its right child point to the child. All right, now for the good stuff. Node 18 has 2 child nodes, and it's really high up the tree. It's the subtree rooted at 18 is the entire tree. But our algorithm still works. We find the successor of node 18 being the smallest value in its right subtree. So even though it's obviously 20, let's go through the algorithm. We follow the right child pointer to go into the right subtree, and then get the minimum of that subtree by just going left repeatedly until we can't go left anymore. The successor then is 20. So we swap these. Imagine an 18 where there's currently 20. 18 in its new position has no children. So deleting it is as simple as severing that link from its parent to it. In practice, writing code, you would access the parent 21 somehow and set its left child pointer to null. I said previously that deleting 20 was going to be easy, and if we deleted these in a different order, that would have been true because 20 had no children. But because of the moving around of nodes that we did due to deleting 18, 20 is now the root. It's now the hardest node to delete from the tree, again. But the algorithm's the same. Find the successor by accessing the right subtree and moving left until you can't anymore. Find the successor 21. Swap 20 and 21. Like, in general, swap the node to be deleted with its successor. And then make it so the pointer from its parent pointing to it is null. And that's the end result of all the operations. Basically, one of the quiz questions. Yeah, I guess I said the cutoff for studying for the quiz was the end of the previous lecture, but this lecture starts out with examples of what we covered in the previous lecture. So I guess that technically contradicts what I was saying. However you interpret that rule, I recommend studying this example at the start of lecture 16. So, zooming out a bit, we were motivated to look at binary search trees in the first place because we wanted a data structure that had super fast insertion, super fast sorting. It's not sorting, it's already sorted. Super fast searching. And we got that through the hash table, but hash tables are kind of bad and evil and hard to use. And also, it was impossible to list the elements of a hash table in a good sorted order without first copying it to another data structure and then sorting it. So compared to binary search trees, hash tables are faster in inserting and searching, and also deletion. But they lack an ability to easily traverse the data structure, to list out its contents in some specific order. So since binary search trees allow for printing out all of the data in some order, we're going to show how it's done. In general, a tree traversal is an operation that visits every node in the tree exactly once in a specific order. I sort of stumbled over my words a bit with the word traversal. The word traversal is specific to trees. It doesn't actually make sense for me to say, well, we want to traverse this hash table. The important part, though, is being able to go through every data item in the data structure in a specific order. Whether or not you call it a traversal, that's impossible, or at least slow, with hash tables. And it's possible via traversals on trees. A better word to use in general would probably be iterate. It is inefficient to iterate through a binary search tree. It is inefficient to iterate through a hash table, but it is efficient to iterate through a binary search tree. Cool. There are 3 standard forms of traversal that we're going to look at: pre-order, post-order, and in-order. And you're soon going to see why they have those names. All of these traversals follow a very similar sort of recursive structure. And in a pre-order traversal, we act on the current node first, and then recursively perform a pre-order traversal on the left subtree, and recursively perform a pre-order traversal on the right subtree. The verb act on is super vague, and that's good. It means it's generalized. For the most part, in this course, when acting on a node in a binary search tree, that just means print its value. You could just mentally replace act on with print. But in a real-world application, act on could mean any sort of method call or action. Say, I don't know if this is a good idea, but if storing users of a website or service in a binary search tree, and you have some property for number of days using the service. I don't know. I don't know why you're not just calculating that on demand based on the local time, but bear with me. If you wanted to go through every user that you're storing in the binary search tree and increment their days using the service variable, you would do one of these traversals, and this notion of acting on it would be incrementing their number of days on the service. Stupid example. Please don't actually keep track of users like that and calculate user ages like that. But I needed to think of something that could be a replacement for act on other than printing. So to traverse a tree, you would call pre-order on the root node. And since the pre-order method would take any node as its parameter, you could theoretically do a pre-order search starting from anywhere. Like maybe you wanted to do something with the bottom half of the list, and you like do a pre-order traversal starting there. Yeah, you could. Oh yeah, look. Assume that the operation performed is to print the data in that node. That's what we're going to do pretty much all the time. So if we call pre-order root in the above tree, we're going to see what order the values are printed. So remember, pre-order would first act on cur node, and then pre-order, do a pre-order traversal. On the left subtree, and pre-order on the right subtree. I got the syntax wrong. Should be kernode dot left and kernode dot right, but this is pseudocode. All of the syntax is wrong. As long as you get the idea behind what the algorithm is doing, it's good pseudocode. I just wrote that down so both of us can reference it while we go through the example. I'm going to put little numbers on here to indicate when we would get to them, and then erase them because the real answer is on the next slide. But yeah, we'll go through this together. We start at the root because we called pre-order on the root. So we act on it. I just put a 1 there to indicate that it's acted on first, but you could imagine a print statement that prints 18 first. And then we're going to do a pre-order traversal on the left subtree. And then how does that one work? We're going to act on the root node. I guess from the perspective of that pre-order call, this would be the first node to be acted on, first one to be printed. But then I could just say that every node is the first node of its own pre-order traversal, and that would be completely unhelpful. So I'll put a 2 there, because this is going to be the second node to be printed. So we acted on cur node, and then we do a pre-order traversal of the left subtree. act on the current node, do a pre-order traversal of the left subtree. Act on the node, do a, oh no, there's nothing here. The real pre-order code would have some way to handle this. As it's currently described, act on current node will have some sort of null reference exception. Oh well, just imagine exception handling in this code. Sensibly, we would say that the pre-order left call terminates when it's called on nothing. So that frees us up to do a pre-order traversal on the right subtree. And that means we're only acting on this node. It is technically a tree because trees can have just one node. And then the two recursive calls, they would both immediately terminate because there's nothing to traverse. So wow, we finally got to the end of this pseudocode by successfully doing pre-order right. So you learned about recursion in first year. What happens next? We sort of go back up through the call stack. And by the way, the call stack is a very appropriately chosen name because it is a stack. This is totally an aside, but when your computer is running your code and you call functions and those functions call their own functions and those functions call their own functions, that's a stack. Like your code is compiled to something that just straight up uses a stack ABT. No idea how it's implemented, but it's cool. So we pop those functions off of the stack. First going back from that leaf node to 2. And then 2 is also done because we just did the pre-order traversal of its right subtree. So we go back to 6. And with that subtree, we just finished doing the pre-order left, and we'll do the pre-order right, which is a matter of acting on the one node in the tree, noticing that there's nothing in its left or right subtrees, and exiting. So now we're back here. The function terminates because we've done a pre-order traversal on both its left and right subtrees. So we're back at 12. The subtree rooted at 12 to be more precise. We just did a pre-order traversal on the left subtree, so we do pre-order traversal on the right subtree. I think I'll speed this up once I get to the right side of the tree, like this stuff. But for now, I'm going to keep explaining every step. Now we're at node 15. And I think number 7. We just acted on the current node. We tried to do a pre-order traversal on the left subtree, but there's nothing there. Go to the right, recurse, visit, or act on that node, do a pre-order traversal of the left subtree, act on this node, try to go to the left and the right, nothing there. Exit. On 17, we were partway through the traversal. We had just traversed the left subtree. We tried to go to the right, nothing happens. So then we exit that function call. From 15, we just finished going through both the left and right subtrees, so we exit. From 12, we just finished going through the left and right subtrees, so we exit. And now we're finally back to the root node. We just finished doing a pre-order traversal on the left subtree, and now we go to the right. I'm gonna go through this a lot faster. But at this point, you still should be able to follow along. Act on this, go to the left. Act on that, go to the left. Act on that, go to the left. Act on that, go to the left. The stack unwinds. It would check out the right children if it would, but it can't. There are no right children. The stack unwinds all the way to 27, and then we go to the right. Act on this, go to the left. Act on that, go to the left. No children, unwind. We had just gone to the left, so we go to the right. Act on that, attempt to go to the left, nothing there. Go to the right. And then we're done. Of course, the computer isn't. It still needs to unwind the call stack, exit the recursive call for 40, exit the recursive call for 39, exit the recursive call for 36, until we're back at the root. We find that we have done a pre-order traversal on the left and the right, and we're done. And then I erase this entire thing because I want to keep this for studying ability, and the right answer is already outlined here. This is identical to the stuff I just wrote down. Another word for a pre-order traversal is a depth-first search. We call that depth first because we go as deep as possible into the tree before moving upwards at all. One neat application of trees that I admit I don't completely understand is making AI for games. Like chess is a good example. You could have a decision tree where each child of a node is a possible move of one of your pieces. It wouldn't be a binary tree, of course. It would have a whole bunch of children because there are a whole bunch of legal moves. But it would be a tree nonetheless, and the idea of a pre-order traversal or depth-first search would still apply. So if you do a depth-first search on a tree representing possible chess moves and their outcomes, a depth-first search would basically simulate an entire game before going back to the last move in the game, seeing if that could have gone differently. And then going to the second last move of the game, see how that could have gone differently. Gradually unwinding the call stack until you go back to the top and do the same thing all over again with a different first move. It's cool. Okay, post-order traversal works similarly to the pre-order traversal. The only difference is that instead of pre, it is post. Pretty good naming convention, gotta give them that. So you do a recursive post-order search on the left subtree, recursive post-order search on the right subtree, And then only after you've done both of those, you act on the current node. Very similar look to the code compared to pre-order, but we're going to get completely different results. Let's walk through them. I'm not going to write down the code again. You could just remember that you do left, right, and then act. So starting from the root 18, we're going to immediately move to the left without doing anything on 18. Likewise, starting at 12 in the recursive call, immediately go to the left. Starting at 6, immediately go to the left. Starting at 2, there's nothing to the left. We can't do anything. Just like with the pre-order traversal, this code would probably just throw an exception and blow up once you get to the bottom of the tree. But we're going to be nice and assume that this represents an algorithm with proper null pointer handling. So, pre-order traversal to the left did nothing, starting at 2. So we go to the right. At 3, both of the traversals do nothing. And then we finally get to act on the node. So if you're printing these in order, 3 would be first. We exit that function call, go back to 2. Since we had just done both of the recursive traversals, we act on this. 2, 2. At 6, we had just finished the left recursive call. Now we just have to go to the right. And then we have that this one actually acts on itself because there's nothing to see in the left and right subtrees. Then on 6, we have just gone through the left and right subtrees, so we act on it. And then for 12, we just went to the left. Now we have to go to the right. And the same thing just keeps happening. Once you know one of these traversals, you kind of know them all. You could probably guess what the code for the next traversal is going to look like. But let's finish up this example first. Oh yeah, so 15, go to the left, nothing there, go to the right. Arrive at 17, go to the left. It's 16. Nothing at the left or the right. So we put it in order. 17, nothing to the right. So I said put it in order last time. Better word would have been act on. 15, we just went to the left and the right. Act on it. Same thing for 12. And then we're back at the root. Poor thing is going to be the last node to be acted on, because next we're going to the right. Repeatedly going to the left, starting at 27, will end us up at node 20. Unwind the call stack. Prints the nodes in this order. And then we're back at 27. Now that we've gone to the left, go to the right. At 36, go to the left. That's going to be the next one to be acted on. We've gone to the left from 36, go to the right. Go to the right. And then now that we've reached the bottom right corner of the tree, all of the nodes are just going to be acted on in order going up. Ta-da! This one has the property that all child nodes are acted on before their parent node, which can be very useful in cases where you're doing some sort of processing on binary search tree data and you have some sort of data that, or such that calculating it for a node somehow depends on the data in its child nodes. Surprisingly hard to phrase, but there's a relatively easy to explain example of this, and that is parsing arithmetic expressions. This is totally extracurricular. I skipped past arithmetic expression parsing the first time because it wasn't necessary, but told you that it still might be fun to go through for the sake of widening your knowledge on these concepts. This is the same thing. I'm going to talk about arithmetic expression parsing to sort of give an example of how this might be used, but you'll never be tested on this specific example. Anywho, a cool way to store arithmetic expressions, and probably something that many calculator apps do, is construct a tree with those operations. So say I wanted to calculate, also where can I get some space? Yeah, I'll draw it here. So I wanted to calculate 3 plus 2 times, I don't know, 9. I'm just going on the order of nodes here. And then to make it a bit more complicated, I'm going to add some more numbers. Minus 6. Sure. Because of how order of operations works, you're going to want to do the multiplication first, and then those addition and subtraction operations. So you could actually structure this as a tree. Oh wait, I'm going to make it a bit cooler. We're going to put brackets here so that the result of the multiplication depends on that addition and subtraction. So you could make a tree with nodes for your operations and leaf nodes for numbers. So this mathematical expression can be expressed by this tree. And then once you have the data structure, that gives you a cool algorithm for evaluating it. You do a post-order traversal. And on the way up the call stack, remember the results of the expressions in the children. And that'll look something like visiting 3 first and just like saving it for plus, and then visiting 2, saving it for plus, and then at that third line, act on cur node. From the traversals, you would already have 3, 2, and plus in memory, and then you could calculate the result. 5. Go up the call stack. You would arrive back at the root, traverse the right side, these number nodes would just return their own value when acted on. And then from the subtract node, you visit both 9 and 6. You would have, I'm going to draw this to be a little more clear. So this subtraction node would use its children's values to do the operation that is contained in it and take on the value that is the result. And then at the multiplication node, we finally reach that after traversing both the left and right subtrees. This turns into 5 times 3, which we all know to be 15. And then this whole expression, assuming I'm doing the arithmetic right, I'm just making up these numbers on the fly and hoping it works. This whole expression equals 15. And that's why you would ever want to do a post order. One more traversal left to go. Only one more possibility even left after those first two nodes. We did one where acting on current node came first. Then we did it where acting on current node went last. And now we're going to have it happen in the middle. The current node is always acted on in between the left and right subtrees, so we call that in order. And let's see what happens. Unlike pre-order and post-order, in-order has a pretty obvious and intuitive reason why you would want to do this. Try to see what it is while I go through the example. Okay, so we start at 18. Our first operation is going to be to do a recursive in-order traversal on the left subtree. Cool. Starting at 12, we do a in-order traversal of its left subtree. Starting at 6, we do an in-order traversal of its left subtree. 2 doesn't have a left subtree, so that function call immediately exits. Then we act on the cur node. 2 will be the first node to be acted on, in this case printed. And then we check out the right subtree. Nothing here, so we just act on it. 3 will be the second one to have that happen to it. The in-order search on 2 returns, so we arrive at 6. Act on that and go to the right subtree. This just gets acted on because there are no children. And then that call returns. Act on 12 and go to the right. 15 has no left child, so we act on it and then go to the right. 17 does have a left child, so we follow it. 16 doesn't have any children, so we just immediately act on it. 17, now that we've traversed the left, we act on it and attempt to traverse the right, but there's nothing there, so we return. And now we're back at the root node, which we act on before going to the right. And I'm just going to do a short pause on this demo because that obvious use case that I mentioned believe it or not, it is visible now. Does something seem weirdly practical about the order in which these numbers are printed? Could it possibly be that they are in order? Yeah. The in-order traversal, it turns out, acts on all of the values in the binary tree in sorted order, ascending order. Like 2 is the minimum value. It's acted on first. Then the next one, 3 is the second to be printed. Then 6, then 9, then 12. These are all in order from smallest to largest. This is exactly the weakness that I described for hash tables. Doing this on a hash table would, as described earlier, require copying it over to an array and then sorting the array and then printing the contents of the array. Binary search trees, we could just do it. Now that we've gone through the left subtree of the root and also acted on the root, we go to the right now. And I could just assign numbers to this, totally eyeballing it. I don't even need to remember the algorithm because I see this property. So I'm just going to go left to right. 20 is the next one, and then 21, then 25, then 27, then 32, 36, 39, and 4. So I just did that without having the details of the recursive calls in mind. I didn't have to. In-order traversal in-order traversal prints all of the data in the tree in sorted order. Should I do this in 8 minutes? Get roughly a minute per slide. I think that we're already ahead enough. We can relax. The next topic before we end our discussion on trees is going to be some math and proving the stuff I was throwing around earlier about all these operations working in O of log n times. Yeah, we're going to look at summations again. It'll be fun. And we'll end up mathematically justifying my claims of this data structure being more efficient than others. But that can wait till after the quiz. In the meantime, good luck. I'll see you tomorrow.